So this work is about client application vulnerability patching and related issues. So let me introduce you a little bit the scenario. Okay. Software vulnerabilities are one of the most critical issues for the security of our computers because they can get exploited, basically, and your machine can get part of a botnet, or your personal data may be stolen. One of the most effective ways against vulnerabilities is patching. If you patch your vulnerability, basically, your machine is going to be safe. So the idea is how to study vulnerabilities. We are used to this life cycle that's basically linear. So you will release your vulnerable application, and then at some point, the vulnerability will get disclosed. Then you will start to patch. And then we will observe, for example, 3 important milestones that are 50, 90, and 95% patching of the vulnerable hosts. So what are the research questions that we are going to ask in this work? So when does the patching start? So what is the delay between the vulnerability disclosure and the start of the patching? How long does the patch deployment take? Basically, how fast the hosts that are vulnerable are going to patch? And what are the factors that are affecting vulnerability patching? So we have found shared code, user categories, basically. Different user categories may patch differently, and exploits. So as exploit, I mean basically the way to how the vulnerability gets patched when the exploit is released, if it gets faster or not. So prior work has studied extensively server-side vulnerabilities. And it's easy because you can scan the internet and basically check that your machine is vulnerable or not. But on client side, you cannot scan. So this is not going to work. There is a prior work on browsers that are client-side applications that basically studied through the network the user agent string of the browsers that were visiting a particular and very popular website. The problem of this approach is basically that if the machines are behind nothing, you cannot really count them. And if the machines are not visiting the website that you are monitoring, you cannot count them. And also, there could be dormant applications that you install on your system that basically you never use. So the problem is that in order to study client-side vulnerabilities, you need to be on the machine. And in order to be on the machine, basically, you need something that will help you to understand which are the applications that are installed in the machine. And in our case, we had access to the Symantec wine binary reputation dataset. And let me explain you how this dataset basically works. This dataset contains 8 million Windows host data, basically the hashes of the file and some other information like the first seen date in the system. So we have the internet users, that is a big set. Then the subset are the Symantec users. Then the users that opted in for the system, it's another subset. Then this data is sampled, and we have the wine users. And we selected 10 popular applications from this data set. So let me show you which are the applications that we will study and why we did it, why we selected these applications. So we selected 4 browsers, 2 multimedia players, 1 document reader and 1 document editor, 1 email client, and 1 networking tool. We selected this application because they're popular. They are from different publishers, so they may have different patching policies. They have auto and manual updates. They are open and closed source. We select and analyze roughly 1,600 vulnerabilities for a period of 5 years over more than 8 million hosts. So what are the main contributions of this work? We analyzed this number of vulnerabilities for 10 applications over a period of 5 years. Then we developed a methodology to map the files on the end host to vulnerable and patched version. And basically, we do a survival analysis that is a statistical technique that is going to tell us how the vulnerability is decaying over time, basically how the vulnerable population is decreasing over time while the applications are getting patched. And we show that the linear vulnerability lifecycle is not descriptive enough to describe some corner cases, for example, shared code, that I will tell you what it is. And we basically developed 2 new attacks, proof of concept, against shared code. We make user categorization, and basically we analyze different user categories, how fast they patch. And we make measurements about the exploitation, basically when the exploit gets available in the wild, and how this affects the vulnerability patching. So let me tell you what is shared code. So we are used to this model that I showed you before. So what happens if you have another line of the application installed? For example, you have Adobe Reader 5 because you installed it with your old printer driver, and you just forget about it. And then you have Adobe Reader 10 because you needed it. So what happens to the patching? Let me show you some scenarios, and then we can go a little bit into the attacks that we have found. So imagine the user has, for example, Adobe Reader, and Adobe Reader has this library that is used to play Flash content, and is in one path. Then you have Adobe Flash that has the same library and is in another path. So basically, you will have 2 libraries, the same code, 2 times in the system. So I let you try to imagine what can happen, what an attacker can do with this setup. So the first problem is basically they will have different patch releases. And of course, different patching programs. So for example, what can happen is, OK, I got the pop-up from the Flash client, from the Flash application. It says, you have to update. I update, and I think I'm safe. And then I forget that I have the same library in another application, and maybe I don't patch it. There is another scenario of shared code that is basically 2 versions of the same application. For example, Reader 5 and Reader 10. And one of the 2 libraries can be vulnerable, and the other one can be patched. So basically, what an attacker can do in this scenario is trying to trigger the old version. So in this model that I have here, the user has Adobe Flash with this library for playing Flash content that is updated. And then the user has Adobe Air, that is a framework to play web applications on the desktop. And on top of this Adobe Air, the user has an FLV player that is an application that basically plays FLV files that are Flash videos. It's just another format for Flash videos. So if the attacker is trying to send to the user an SWF file, this will hit the Flash player that is patched. So nothing is going to happen. But what happens if the user sends an FLV file that is automatically associated with the FLV player? I let you imagine what can happen. Basically, it can get exploited. We have also another attack, and I suggest you to check the paper, because we didn't have time to explain it here. So let me show you how we did this study. We had access to different datasets. Mainly, the most important one is the wine binary reputation dataset that gives us the files that are installed on the user machines. And then we enriched this dataset with the metadata from VirusTotal. Basically, 70% of the files in the wine binary reputation are also in VirusTotal. So we could enrich this data with more information, for example, the developer, the publisher, and all this kind of information. From these files, we basically associate them to the National Vulnerability Database and open source vulnerability database in order to see which are the vulnerable versions for a given vulnerability. And then, thanks to the Symantec Wine AV dataset and exploit.db, we basically check the exploit release date, and we see how the vulnerability patching is affected when an exploit is released. So let me show you a little bit the pipeline that we have. So the first thing is that you have to associate a list of hashes to a real installation of an application on the client machine. So the idea is you have to find a way to understand if the users had the application installed. So the idea is some applications constantly use the same file name for the main executable, for example. Firefox.exe is an example. So all the version of Firefox will have firefox.exe. And this file keeps updating its version when the new releases are released. And then we have another interesting piece of data that is the first scene. So when the application appeared in the dataset. Then with this data, we associate it in the National Vulnerability Database and Open Source Vulnerability Database to find which are the vulnerable versions for a given vulnerability. So this is an example. You see the CVE, and then you have the versions. So I put the arrows there because one of the issues that we have found in MVD is basically that you have the program version that is, for example, advertised, but is not the exact file version. So, for example, Firefox 3 corresponds to the file version 1.9.3. So this is an issue because we couldn't find all the mappings for all the applications. So we also found other errors in the MVD, for example, missing vulnerable version or extraneous, so versions that are not vulnerable that are reported as vulnerable. Then we cluster together vulnerabilities that patch with the same versions in order to minimize the amount of work. And then we perform survival analysis. That is a statistical technique that allows us to measure how the vulnerability is decaying over time. This technique is used in life science to basically test the survival of the patients for a new drug. So basically, in this case, we use this technique to measure how the vulnerability are decaying. And this is an example. So these are two vulnerability clusters for Google Chrome. And as you can see, the red cluster is decaying, and it reaches 90%. Let's see if I have the laser pointer. No. OK. The vulnerability is decaying, and after 50 days, is reaching 90% of the patching. But for example, the other vulnerability cluster will reach the 90% after more than 200 days. And this could be due, for example, to unused application that you have installed in your system. So let me show you some results. In this table, I show you basically the second column is the patch delay that takes from the vulnerability disclosure. And as you can see, there are negative values. What this means? It means that some application starts to patch before the vulnerability disclosure. This because probably the developers already know the problem, and they start to patch before the vulnerability disclosure. Then we have the two milestones that are how the patching evolves over time. For Google Chrome, that had automatic updates since its beginning, it takes only 15 days to reach 50% of the machines for 100% of our cluster. But it takes more than 200 days to reach the 90% milestone. But it's still the fastest application. On the other hand, if you see Wireshark, that during our observation period had completely manual updates, it doesn't reach any milestone during our observation period. Now, I will show you how the shared code impacts the vulnerability patching. So this is another plot of survival analysis. But as you can see here, we have two applications and the same vulnerability. So the idea that should pop up in your mind immediately is that these two lines should overlap because it's the same vulnerability, but they are patched differently. So what we have found is that we have found 80 vulnerabilities in applications that are sharing code, and the median difference between the patching is 11 days. But we had the extreme case that is the maximum, that two applications with shared code had a difference of patching of 118 days. So now I will show you what we have done in order to see if the user category influences the patching rate. So we have identified different user categories. This is a picture for all the users. Then we have software professionals, developers, and security analysts. How we selected them? Based on the application that they use. For example, the software professional will use applications like SAP or Citrix, while The developers will use Eclipse, NetBeans, Visual Studio, Subversion, Mercurial, and the security analyst is going to use IDA Pro, Wireshark, OllyDBG. So all the users patch in a median time of 45 days. Then the developers in 24 days, the professionals in 30 days, and the security analysts in 18 days. So this could really help cyber insurance, because with this profiling, you can basically design a tailored policy for each user category. And now let me show you how the exploits impact on the vulnerability patching. In this plot, you can see the same survival analysis, but we reported the number of days after the patch is released when the exploit appeared in the wild. And basically, we found that only 14% of the hosts are patched when the exploits are available. We did this only for 54 vulnerabilities, because we could find the release date only for 54 exploits. So wrapping up, what we have done in this work. Basically, it would be really interesting to consolidate the patching mechanism. It means if you have shared code, it's needed to have a single application that will handle it. And of course, having an installer that is going to check if you have a prior version and is going to uninstall it. If you install a new version, it would be really helpful. And also, we propose a wild idea that could be basically managing updates for library in a different way with separate applications. So in this work, we have analyzed roughly 1,600 vulnerabilities for 10 applications over a period of 5 years. We showed that the linear life cycle for vulnerabilities is not descriptive enough, especially in case of shared code. We developed 2 new attacks against shared code. We measured which is the user impact based on categories on the patching delay. And we propose a general technique to map the files and realize survival analysis. So thank you very much. I will take questions now. And please, if you are interested to see the errors that we have found in the NVD, please visit clean-nvd.com. Thank you very much.
Thanks, Antonio. We have time for 2 questions.
Hi, Cami Vanya, Indiana University. You were mentioning the average time to patch for the various groups. I'm curious what the ranges looked like. So were users more, or normal users more inclined to cluster around that mean, or are you seeing a very wide range? Essentially, what do the standard deviations look like for those different groups?
No, sorry, I didn't understand your question.
I imagine end users do not all patch at 45.
Can you speak loudly, please? Can you speak loudly? Because...
OK. I imagine end users do not patch at all at 45 days. So there's a range, right? There's a standard deviation.
Yes.
I'm curious what the standard deviation differences are between the groups. So are you seeing differences between developers in their range of times to patch from end users?
Well, I think the difference is not really huge. So basically, the median that we have measured is saying more or less what we have observed. So there is not a huge difference between the user categories. The difference is that the groups of users are different. The size of the groups of users are different. So there are less security analysts, there are less developers, but the data, I mean, it's not really different.
Thank you.
So I just have one quick question. So how did you go about picking the applications? I didn't see Java on that list, for example. So why didn't you pick Java as, I mean, it's one of the most exploited applications.
Well, I think we selected the application also based on what was the availability of the main executable, because when you install Java, maybe the version is not included in the file that is the main executable, so you cannot track how the versions are evolving over time. That's basically why we didn't select Java, for example, because maybe the main executable is not reporting the actual version of the file, so we cannot associate it with the, because the problem is you have Java 7, okay, and then in the NVD you will see Java 7, and you don't know to which file version it corresponds. So that's why we didn't select it.
Okay. Let's thank the speaker again.